Hello, this is Silas Gross, and this is my Lab 3 going over the gravity of bodies in motion. The purpose of Lab 3 is to observe the motion of an object due to gravity, with Part 1 being to analyze the star's motion in order to find the mass of the black hole, and Part 2 to be to examine the relationship between three bodies in motion. Introduction of the key terms is that we'll be using the GlowScript computational model for this. We'll be using force perpendicular, force parallel, the velocity and position update formula, and Newton's law of universal gravitation. So the key principles are force parallel, force perpendicular, the net force, the velocity position update formulas, and the force of gravity. The experiment itself is that we used the perpendicular force to get the centripetal force. We calculated F net with change of momentum over time. We used F parallel to get F net minus perpendicular, and that found us the force parallel. We used the update formula to get the path of the starship based on the found forces of gravity. For the systems and surroundings, for Part 1, we used the system as the star, the surroundings being the black hole, and the initial conditions being the mass of the star and delta T. Part 2, the system was the rocket ship, the surroundings were the planet and the moon, and the initial conditions were the velocity we inputted, and then the masses of the ship, planet, and moon were given. The experiment itself was done on the computational models. Here's Part 1. Important parts of Part 1 are defined P initial is just velocity times mass, the same for P final. Deltas is just the final minus the initials. The change is the delta over the delta time, F net being what was found from that. Define P hat, U norm, the P initial. Here's the formula for the magnitude. And then we find our force parallel here. From force parallel, we can find the force perpendicular if we know force net. And then the mass of the black hole is just changing around the force due to gravity equation, where this is raised to the power of 2. And then if we run this, we can see that our net force is the orange arrow. It's always pointing towards the mass of the black hole. Our cyan arrow is our force perpendicular. It's always pointing towards the center of the circle. And there's a tiny arrow that was going to be our force parallel. It's a lot smaller than these two because for most of the time, these two are pointing in roughly the same direction. If we move on to our Part 2, we can see that the main equation here is looking at, once again, our force due to universal gravity. Here, this is just the magnitude raised to the power of 2. Hat is pretty much the same as norm. We find it for all of the different ones, and then we find our F nets. We don't find the F net of anything on the planet because the planet's mass is so much larger than everything else. Here is our position update, our velocity update. Here's our position update. Same for the ship. And then we can find our speed for x and our speed for y by looking at where the forces due to gravity are roughly equivalent. We can also plug it in, and from that information move around and try and find different ones. This is what I found to work the best. We can see that this sharp turn here shows that the rocket ship started orbiting around the moon, and then these circles show that it's orbiting mostly around the planet itself. When these circles change in size, it's showing that it was being impacted by the force of gravity from another body, that being this moon. We can see that now this circle is much smaller than it once was because it was so close to the moon. It was behind it, slowing it down. We can see that this is not the only time that this is impacted. Later on, it will also be orbiting around the moon, like right there. This happens again, and then doesn't crash for this entire time. This will eventually crash somewhere around 900 hours, but for our purposes and our intents, it didn't crash here. The differences and the similarities are this is just a computational model. You're not really going to be able to find this in the real world. This is a possible speed for a spaceship, though. Our initial velocity was, in fact, smaller than the largest velocity a rocket ship can have. This is all theory-based, so the only really possible error would be if I wrote an error in my code. I don't think that's happened, but weirder things have occurred. What if questions? For the first one, the rate of change of the momentum is the net force. From this, the rate of change of the momentum parallel is the force parallel, and the rate of change of the momentum perpendicular is the force perpendicular. And then if a black hole was to be considered for a Part 2 model, we would need to find the force of gravity of the black hole on the ship, the moon, and the planet. And since the mass of the black hole is so large, we wouldn't really need to consider the effect of any other body on the motion of the black hole, unless we need to be incredibly precise. The ratio of the mass between the black hole and anything else is just going to be too large. Thank you for your time.